All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones. Today, what are we doing? We're doing multivariable calculus. We're doing Chapter 1, partial derivatives. We're in specifically section 1.7, which is local extrema and saddle points for functions of two variables. And then this lecture, what we're going to do is continue with the second derivative test. Then we're going to do extreme value theorem for a function f of x, y. Let's do that. For example 1, we'll go back to a fairly simple as we can get for surfaces in 3 dimensions. We're going to look at an elliptic paraboloid with the center 2, 1, 4. We've hidden it here, so first of all what you want to do is put that in standard form so that I can see where the center is. How do I do that? I need to complete the square on x and y. So doing that, I see f of x, y is actually equal to x squared minus 4x plus what do I need? What I'm going to do is write 9 as 5 plus 4 right now for a second. And then I'm going to steal one of those. So I'm going to write plus 4 is what I'm stealing from the 9. And then plus I have y squared minus 2y. And then I need a 1. So actually I'm going to write that as 4 plus 1 is how I'm going to write 1. And then I stole the 1 and I stole a 4. So I have 4 left. Why have I done that? You can add in and subtract it in, but then you're going to just subtract from the 9 and get a 4 anyways. Either way, I'm completing the square. These are now perfect squares. That says f of xy is equal to x minus 2 squared plus y minus 1 squared plus 4. And then z equals f of 2, 1, which is equal to 4. So this gives us the center 2, 1, f of 2, 1, which is 4, which is on our curve right there. That guy. It turns out even from the picture, that's why I'm drawing it, from the geometric avatar, it seems like we have one local minimum, which is actually an absolute minimum, and it happens at 2, 1. We now want to use the first, so I can do that brute force actually. If we notice that f of 2, 1 is 4, and then if we also notice now that f of xy is equal to x minus 2 squared, I don't care what x is, that thing is positive, plus y minus 1 squared, I don't care what y is, that thing is positive, plus 4 is greater than or equal to, even if this is 0 and this is 0, it's either 0 or greater than that, so that's greater than or equal to 4, which is what? 4 is f of 2, 1. What we just showed is for every x, y in the domain of f of x, y is greater than or equal to f of 2, 1. What does that say? From our definition in our previous video, that is an absolute minimum for a function. This says f of 2, 1 is an absolute minimum. That wasn't even first or second derivative test. That's just me using algebra for a function of two variables. It's not too bad, so I can control it and I can argue something. Let's actually use the first or the second derivative test now. I need the first derivatives. Fx from here is going to be 2x minus 4, and fy is going to equal 2y minus 2. When are those going to equal 0 is what I want to know. That tells me that I will get exactly x is 2 and y is 1. Oh, those guys. So that gives me the point 2, 1. That's my only critical value, or point. It's not a value anymore. Point in 2 space. Once I have that, first of all, I assess the first derivatives are polynomials in x and y, therefore they exist for the entire domain r squared, or the entire region r squared, and therefore it's continuous everywhere, and so, or it exists everywhere. The first derivatives exist everywhere, so the only place I could have a critical number is where they're 0. I then say, when are those 0? That happens when x is 2 and y is 1, so the only critical points I can have is at 2, 1. And then what am I going to argue? I'm going to argue the same thing I just argued last time, that every other point is larger than that. How do we do that? Using the first derivative test. We show that the discriminant is positive and the first derivative is positive, and that gives us a minimum. Let's do that. Now we have to compute fxx is equal to 2, fyy is equal to 2, and fxy and fyx is equal to 0. that tells us that fxx is 2, which is greater than 0. And the discriminant, which is this times this minus this squared, is equal to 4, which is greater than 0. So those two things say local minimum. And that's how I use the second derivative test. The second derivative test can only show us that we have local maximums and local minimums. To argue that we have an absolute minimum, we're going to either have to use the similar argument we used previous to show that for every other point that it is larger than 4, which is f of 2, 1, or we can use the next theorem, which is going to be the extreme value theorem for functions of two variables, but you have to be on a closed and bounded region in R2, and then you can argue that you have a maximum and a minimum value. Let's do that. I lied first. Let's do one more example, and then we'll do the extreme value theorem. But remember, this can only find local max-mins or saddle points. To argue that they're absolute, you have to use another additional argument or use a closed and bounded region and use the extreme value theorem. For this one, to find local max-mins, what again I need are the first order derivatives, partial derivatives. Here I get 4x cubed minus 4y, which is equal to 4x cubed minus y, and fy is equal to the same thing, but different. 4y cubed minus 4x, which is 4y cubed minus x. Those are polynomials and two variables. They are existing everywhere in R2. Therefore, the only place I can have critical values is where these things are 0. So setting fx equals 0 and fy equals 0, this gives me x cubed equals y and y cubed equals x. Plugging those into each other, that is going to give me, putting this inside here is going to give me x cubed minus or equals x. So I'm going to get x cubed equals x is what I've just done. Remember, this is a system of two equations and two unknowns with their nonlinear equations. So what do? Hopefully you can solve for one in terms of the other, plug it into the other one, and solve the nonlinear equation. When now, we have an order 9. Can we factor it? Yeah. Oh, yay. Pre-calculus. What? Factoring. This is x to the 9 minus x equals 0. Factoring x out is step 1. This is if and only if I get x to the 8 minus 1 equals 0. Oh, that's x to the 4 squared minus 1 squared. So this is equal to, we get if and only if x to the 4 plus 1, x to the 4 minus 1 equals 0. This is still a difference. That's squared. That gives me if and only if x to the 4 plus 1 is x squared plus 1, x squared minus 1 equals 0. Oh, that's still a squared. And then I'm going to get factoring x to the 4 plus 1, x to the squared plus 1, x plus 1, x minus 1 equals 0. This is an irreducible. This is, well, it has no real roots, but still what you're going to get. You could reduce that into two factors, but either way, this has no roots, this has no roots. This is the w. This is x squared plus 1 looks like this guy. This guy is going to be, I don't know if he has switches or not, but he's sometimes a w. Either way, he's not going to touch the x-axis. I don't know what he looks like. That's not what he looks like. And then, where's the roots? This one, and this one. So this says x equals 0 or plus or minus 1. From that, because y equals x cubed, you're going to get exactly the same things. When x is 0, y is 0. When x is 1, y is 1. And when x is negative 1, y is negative 1. So you're going to get 3 points, 3 critical points. From setting these two guys equal to 0 and solving those two nonlinear equations in x and y, we get 3 critical points, 0, 0, 1, 1, and negative 1, negative 1. What are we going to do with those guys now? We have to identify each of those as being local max, a local min, or a saddle point. How are we going to do that? First of all, what we need is fxx, which is going to be, from here, we're going to get 12x squared. And then we need fyy, which is going to be, from here, we're going to get 12y squared. And then we need fxy, which is going to be the derivative of this one with respect to y, which is going to be negative 4. That means our discriminant in general is fxx times fyy minus fxy squared, which is going to be 12x squared times 12y squared minus 4 squared, which is 144x squared y squared minus 16. Now what do I have to do with that guy? I have to put these in here for each one. What I needed was the first derivatives. From the first derivatives, I need all the second order partial derivatives. And once I have that, I can build D. Once I have D, I can erase everything. And then D, you put these 3 points into D and find out whether fxx is positive or negative and whether D is positive or negative. And then we decide whether we have saddle points or not. What do I need to keep? I need to keep fxx is 12x squared, which is monotonically always positive. I don't care what x is, he's positive. And then I need the points 0, 0, and 1, 1, and negative 1, negative 1. And we need the discriminant d, which is 144x squared y squared minus 16. If I get that, what happens? I'm going to get, at the point 1, 0, 0, we get that the discriminant d is equal to 144 times 0 squared minus 16, which is negative 16, which is less than 0. The discriminant is less than 0. That says what? We have a saddle point, and you don't need fxx. 2, at 1, 1, we get that d is equal to 144 times 1 squared minus 16, which is what? Positive. And therefore fxx is 12 times 1 squared, which is also positive. So that gives me what? Positive. Positive gives me local minimum. And then at negative 1, d is equal to 144 times negative 1 squared minus 16, which is also positive, and fxx is going to be 12 times negative 1 squared, which is still 12, which is positive, so we get a local minimum at this value also. What does that say? We got 2 local minimums and a saddle point at 0. Let's sketch what that looks like. Okay, so what we need, again, to recap when you're doing these ones, I need D, the discriminant D, or the Hessian, which is this guy. I need the 3 critical numbers, which I got from calculating when the first derivatives are 0 or don't exist. And I need the second derivative. If I get the discriminant as negative, that's what you should calculate first always, this discriminant at the point. If I get that's negative, I get a saddle point immediately. If I get at those points that the discriminant is positive, and then I have to calculate and check fxx. In our case, we already knew it was always positive anyways. So when they're both positive, we get a local minimum. And again, when they're both positive, we get a local minimum. Now you can see pictorially, we have a local minimum at this point, negative 1, 1, and 1, 1. And then we have the, I think my axis should be rotated slightly, but whatever, close enough. Don't prove by picture. And then we have a saddle point at 0, 0. All right, so the extreme value theorem for a function of 2 variables, basically it says the same thing for a function of 1 variable. It guarantees you can find an absolute minimum value and an absolute maximum value for a function, but it has to be on a closed and bounded a certain type. It can't be open. And so we're not going to get into it, but the first one we're going to do, this is the first example we're going to do. You can see the surface. What they're saying is, and why I picked it nicely, is because there's going to be 5 values I have to compute. First of all, there's going to be 1 local minimum or critical point for our function. It might be a minimum or a saddle point, we'll find out. And then there are boundary values along this boundary of this region D. What it's saying is along either the boundary of this square or the boundary of your region, or at critical numbers, so the local max and mins, when you gather all those together and compute f at the critical values, and then you compute f at the boundary values, you pick the largest value, there has to be a maximum value somewhere in there, and there has to be a minimum value in those calculations. Here we have exactly 5. You can see that there's, and what this says is the value is unique, but the location in which that happens can happen in more than one value. Again, for in one dimension, sine has infinitely many maximums and infinitely many minimums. or occurrences of them. There's only one minimum value, -1, and there's only one maximum value, +1, but it happens infinitely many times. Same thing here. There's going to be the unique minimum value z equals 0, but it happens at these 2 points. And there's going to be, and then at the other points on the diagonal of the square, at these 2 points, the one right there that you can't see behind the surface, those, if you go up, give us these 2 points, which are going to give us the maximum for the function, but it happens at 2 spots. So the value is unique, absolute value and absolute minimum, these guys, but it can happen at more than 1 point, x1, x2. Let's do the example specifically. If we're going to use this extreme value theorem for a function of 2 variables, we are given a function 2x plus y minus 3xy. And what it wants is it wants us to find the absolute maximum, which is guaranteed by the theorem, and the absolute minimum, which is guaranteed by the theorem, but not for the surface in general necessarily, but on the unit square. The unit square is closed and bounded. And for us, what that gives us is it says x is between 0 and 1, and y is between 0 and 1. And this is our region D, which is the unit square. This is what we're going to be saying that we have to have, because it's closed and bounded, whatever that means. This is our region D now, and more importantly, we're going to have to look at the 4 boundary pieces of that region D and find the maximum values for our function f on all of these line segments. And then we find the maximum values, or we find f at all of our critical values, and then the largest values are maximum, and the minimum is our small absolute minimum, and just like for functions of 1 variable. Doing that, what do I need? First of all, I need fx is equal to 2x minus 3y, and fy is equal to 1 minus 3x. We see that those are polynomials of 2 variables, so they exist everywhere. Therefore, the only way that they can be critical points is if they're 0. So setting those equal to 0, we immediately get that from this one, I get x is 1/3. And then solving for y, if I get 2 times 1/3 times 3, equals 3y, is what I'm doing. And I'm going to get what? 2/3 times 1/3 equals y, so x is 2/9. With these, that gives us the point 1/3, 2/9. And at that value, what we're going to do is, remember, at the end, right, this says our only critical point is 1/3, 2/9. So we have to keep that. Step 1 is find all your critical points, and then at the end we're going to evaluate f at the critical points and on our boundary places. Let's do that now. Once I've found all my critical points, I now have to, and this is what's much more difficult in general for a general region, on the boundary of an interval, it's the endpoints. The boundary of a closed and bounded region here now is going to be these 4 line segments, which we're going to have to analyze. And then we're going to have to do the extreme value theorem for functions of 1 variable, one at a time for those functions, and find the maximum for those functions of 1 variable on the boundaries. And then those largest values are absolute max, the smallest values are absolute minimum. What does that mean? At our critical number 1/3, 2/9, f of 1/3, 2/9 is equal to what? Oh crap, here we go. We're going to get 2 times 1/3 plus 2/9 minus 3 times x, which is 1/3, times y, which is 2/9. That's going to give me, those will cancel off nicely. This gives me 2/3 plus 2/9 minus 2/9. Oh, that didn't seem to be so bad. Zing, zing. This gives me 2/3. What does that tell me? F of 1/3, 2/9 is equal to the value 2/3. This guy. Then what do I have to check? I have to check the boundary. Now computing, what do we need to do to find use the extreme value theorem for a function of 2 variables to find the absolute max and the absolute minimum? I find the critical points. To do that, I find the partial derivatives and where they don't exist or where they're zero, I only got one critical point. The value of the function at that critical point is 2/3. And then what I have to do is look at the boundary regions. In the boundary, there's 4 for our set because it's the unit square. This one specifically, this one, and then there's one hiding behind there. On those, we look and we now have a function of one variable in each scenario. Because we have that, we now can use the extreme value theorem for functions of one variable. These are all closed intervals. Because I have those closed intervals, I have to have an absolute max and min on there. So I compute those. I get the max value and the min value in those. Because they're all monotonically increasing, they're all linear. It's just at the endpoints, which is nice and easy. And then I look, and now all we have to do is pick the largest value in this list. And then we have to pick the smallest value in the list, which happens to be the 0. And then everybody else doesn't really need one, or these ones were the intermediate ones that I didn't need. And that tells me what my absolute minimum for f on this disk is 0, and the absolute maximum on this interval is 2. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of other ones. I'll see you next time.